Welcome to our channel, where we bring you the most interesting and informative content from around the world. Have you ever looked up at the night sky and wondered, why is space dark, even though the sun is so bright? It's a question that has puzzled humans for centuries. After all, Earth is bathed in sunlight during the day, and our night sky is dotted with twinkling stars. Yet, space itself remains a vast, black canvas. The answer lies in understanding the fundamental difference between Earth and space, the presence of an atmosphere. Our atmosphere, a delicate layer of gases surrounding our planet, plays a crucial role in scattering sunlight and illuminating our world. Imagine throwing a handful of glitter into a sunbeam. The glitter particles scatter the light, making the beam visible from all directions. In a similar way, our atmosphere is filled with tiny particles like nitrogen and oxygen molecules, as well as dust and water droplets. These particles interact with sunlight, scattering it in all directions. This scattered light is what makes our sky blue during the day and creates the vibrant colors of sunrise and sunset. Earth's atmosphere is more than just the air we breathe. It's a shield that protects us from harmful radiation, and the reason we see a bright blue sky. The atmosphere scatters sunlight. Blue light is scattered more effectively, making the sky appear blue. This effect also creates stunning reds and oranges at sunrise and sunset. To truly grasp the concept of scattering, picture a single ray of sunlight entering our atmosphere. This ray, composed of all the colors of the rainbow, encounters countless tiny particles in the air. These particles act like miniature mirrors, reflecting and redirecting the light in random directions. This process of redirection is what we call scattering. Now, here's the crucial part: different colors of light are scattered differently. Blue and violet light, having shorter wavelengths, get scattered much more than their longer wavelength counterparts like red and orange. Imagine a game of billiards, where the white ball represents sunlight and the colored balls represent different wavelengths of light. When the white ball strikes a colored ball, the energy transfer is more efficient for smaller, lighter balls. Similarly, blue light, being lighter, gets scattered more easily by air molecules. This preferential scattering of blue light is what paints our sky with its characteristic hue. As sunlight streams through the atmosphere, blue light gets bounced around like a pinball in a machine, filling our sky with its vibrant color. Sunlight, the lifeblood of our planet, embarks on an incredible journey from the sun's surface to our eyes. This journey, spanning millions of miles across the vacuum of space, takes a dramatic turn as it encounters Earth's atmosphere. In the vast emptiness of space, sunlight travels in straight lines, unimpeded by any obstacles. However, upon entering Earth's atmosphere, it encounters a myriad of air molecules, water droplets, and dust particles. This encounter marks the beginning of a fascinating interplay between light and matter. As sunlight collides with these atmospheric particles, it undergoes a process called scattering. Imagine a beam of light as a stream of tiny marbles. When these marbles hit an obstacle, they scatter in various directions. Similarly, sunlight, upon striking atmospheric particles, gets redirected and dispersed. This scattering is not uniform, it depends on the size of the particles and the wavelength of light. Section 5: The vacuum of space, where light travels freely. Space, unlike Earth, is a near-perfect vacuum. This means it's almost entirely devoid of matter, those tiny particles that make up our air, water, and everything we see around us. In the vast emptiness between stars and planets, there's virtually nothing for light to interact with. Imagine a single ray of sunlight traveling through space. Without any air molecules to scatter it, the light continues on its path, unwavering and undeterred. It's like a spaceship gliding through the cosmos, encountering no resistance. This is why stars, those distant suns, appear as pinpoints of light in the night sky. Their light travels millions of miles through the vacuum of space, reaching our eyes without being scattered or diffused. The absence of an atmosphere in space has profound implications for how we perceive the universe. Without air to scatter sunlight, the sky would be black, even during the day. Section 6. Darkness in the void, why space appears black. Space, despite being filled with countless stars, appears black to our eyes. This stark darkness is a direct result of the absence of an atmosphere in the vacuum of space. Without an atmosphere to scatter sunlight, there's no medium for light to bounce around and illuminate the void. Imagine yourself standing in a vast, darkened room. Even if there are light bulbs scattered throughout the room, if there's no air or dust to scatter the light, you'll only see the bulbs themselves, not the space between them. Similarly, in space, starlight travels in straight lines from its source to our eyes. While countless stars emit light, their vast distances and the lack of scattering mean that most of this light travels past us unnoticed. This is akin to shining a flashlight in a forest at night. You'll see the illuminated spot where the beam hits, but the surrounding trees remain shrouded in darkness. Section 7. Stars in the distance, shining bright, yet so faint. The stars we see in the night sky are colossal balls of burning gas, emitting immense amounts of light and heat. Yet, from our vantage point on Earth, they appear as faint pinpricks of light against the black canvas of space. This apparent faintness is a consequence of the vast distances involved. Light from even the closest stars has to travel trillions of miles to reach us. As light travels through space, it spreads out, becoming less intense. Imagine holding a candle close to your eye and then moving it farther away. The flame appears dimmer as the light spreads out over a larger area. Similarly, starlight, despite its initial intensity, diminishes in brightness over astronomical distances. Furthermore, interstellar dust and gas can absorb and scatter starlight, further reducing its intensity by the time it reaches us. Section 8. Earth's glow, reflecting sunlight from afar. Have you ever looked at pictures of Earth taken from space? Our planet, a blue marble suspended in the blackness, stands out as a beacon of light. This glow, visible from millions of miles away, is not Earthlight, but reflected sunlight. Just like the moon reflects sunlight to illuminate our night sky, Earth reflects a portion of the sunlight it receives back into space. This reflected light, a combination of sunlight scattered by our atmosphere and light reflected from our planet's surface, is what gives Earth its ethereal glow. Imagine shining a flashlight on a mirror in a dark room. The mirror reflects the light, illuminating other objects in the room. Similarly, Earth acts as a giant mirror, reflecting sunlight and making its presence known in the vastness of space. This reflected light is not only a testament to the power of our sun but also a reminder of the delicate balance that sustains life on our planet. Section 9. The moon's tail, a familiar example of light and dark. The moon, our celestial neighbor, shows the interplay between light, shadow, and no atmosphere. Unlike Earth, the moon has no atmosphere. This results in a stark contrast between light and shadow. The lunar surface appears dazzlingly bright during the day. Step into a crater's shadow, and you're in absolute darkness. Without an atmosphere, there's no indirect illumination. Section 10. Appreciating our blue sky, a gift from scattering. The next time you gaze up at the azure expanse of the sky, take a moment to appreciate the intricate dance of light and matter that creates this breathtaking view. Our blue sky, a constant presence in our lives, is a testament to the remarkable phenomenon of atmospheric scattering. Without an atmosphere, our sky would be as black as the night sky, even during the day. It's the scattering of sunlight by air molecules, those tiny particles that make up our atmosphere, that paints the canvas above us with its vibrant hues. Imagine a world without a blue sky. The sun, a stark white disk against a black backdrop, would cast harsh, unforgiving shadows. The world would feel alien and desolate, devoid of the soft, diffused light that characterizes our planet. Our blue sky is not just aesthetically pleasing, it plays a crucial role in supporting life on Earth. It filters out harmful radiation from the sun, regulates our planet's temperature, and even influences weather patterns. Section 11, Conclusion, the universe's duality of light and dark. The contrast between the brightness of Earth and the darkness of space highlights a fundamental duality in our universe. Light, the essence of energy and visibility, coexists with the vast emptiness of space, where darkness reigns supreme. Earth, enveloped in its life-sustaining atmosphere, basks in the scattered glow of sunlight, while space, a near-perfect vacuum, remains a realm of darkness punctuated by the distant twinkle of stars. This contrast underscores the unique and precious nature of our planet, a haven of light and life in the vast cosmic ocean. As we continue to explore the universe, unraveling its mysteries and searching for other worlds like our own, we gain a deeper appreciation for the delicate balance of factors that make Earth so special. Our blue sky, a symbol of life and vibrancy, serves as a constant reminder of the intricate interplay of light and matter that shapes our universe. Beneath our feet lies a mystery. It's a place we can never visit, hidden by layers of rock and metal. This is Earth's core, a sphere of iron and nickel larger than the planet Mars. The core is divided into two parts. The outer core is liquid metal, constantly moving and churning. The inner core is a solid ball of iron, under immense pressure and heat. Though hidden from view, the core plays a vital role in our lives. It's the engine that drives Earth's magnetic field, our shield against harmful radiation from space. Earth's core isn't static. The inner core spins, and the liquid outer core flows around it. This movement is driven by heat escaping from the core, creating swirling currents of molten iron. Imagine a pot of boiling water. Heat from the stove causes the water to move, creating currents that rise and fall. The core's movement is similar, though on a much grander scale. This constant motion within the core is what generates Earth's magnetic field. Like a giant dynamo, the flowing metal creates electrical currents, which in turn produce a magnetic field that extends far out into space. Earth's magnetic field is our invisible protector. It acts like a shield, deflecting most of the charged particles streaming from the sun, known as the solar wind. Without the magnetic field, these particles would bombard our atmosphere, stripping it away over time. Mars, which lost its global magnetic field billions of years ago, suffered this fate, leaving it with a thin atmosphere and a dry, desolate surface. The magnetic field also protects life on Earth from harmful radiation. Cosmic rays, high-energy particles from deep space, are deflected by the magnetic field, preventing them from reaching the surface and harming living organisms. What would happen if Earth's core suddenly stopped rotating? It's a scenario explored in disaster movies, but what does science say? While it's unlikely to happen overnight, a gradual slowing of the core's rotation is possible. In fact, some scientists believe the core may be in the process of slowing down right now. If the core's rotation were to stop completely, the first and most immediate effect would be the weakening of Earth's magnetic field. Without the dynamo effect of the flowing outer core, the magnetic field would gradually decay. Section 5, A World Without a Compass. A weakening. Magnetic field would have a cascade of effects, some more immediate than others. The Earth's magnetic field is a crucial component of our planet's ability to sustain life as we know it. Compasses, which rely on Earth's magnetic field for navigation, would become unreliable, pointing in random directions. This seemingly simple tool has been a cornerstone of human exploration and travel for centuries. This might seem like a minor inconvenience, but it could have serious implications for navigation, especially in remote areas where modern technology might fail or be unavailable. Particularly for ships at sea and aircraft in the air. These vessels often traverse vast, featureless expanses where traditional landmarks are non-existent. Modern navigation systems rely on GPS, which is a network of satellites orbiting the Earth. However, these systems are not infallible. But a backup system based on traditional compass navigation is always crucial. In the event of a GPS failure, having a reliable compass can mean the difference between safety and disaster. Animals that use Earth's magnetic field for navigation, such as migratory birds and sea turtles, would also be affected. These creatures have evolved over millennia to rely on the magnetic field for their long journeys. Their ability to navigate across vast distances could be disrupted, potentially impacting their survival. The loss of this natural navigation system could lead to disorientation, failed migrations, and even population declines. Humans, too, are more dependent on the Earth's magnetic field than we might realize. Beyond navigation, the magnetic field protects us from harmful solar radiation. Without it, the planet would be bombarded with high levels of radiation, which could have devastating effects on our health and the environment. Historically, the Earth's magnetic field has undergone changes, including reversals where the magnetic north and south poles switch places. These events, while rare, have had significant impacts on the planet. As we look to the future, understanding and preparing for the implications of a weakening magnetic field is crucial. It is not just a scientific curiosity but a matter of global importance. Scientists around the world are studying these changes, using advanced technology to monitor the magnetic field and predict its future behavior. Global efforts are underway to mitigate the potential effects, ensuring that both human and animal life can adapt to these changes. While the challenges are significant, there is hope that through innovation and collaboration, we can navigate a world without a compass. Section 6. Cosmic Rays Run Wild. As the magnetic field weakens, Earth becomes more vulnerable to cosmic rays. These high-energy particles can penetrate deep into the atmosphere, increasing radiation levels on the surface. While the increase in radiation wouldn't be immediately life-threatening, it could have long-term consequences for human health. Exposure to elevated levels of radiation can increase the risk of cancer and other health problems. The impact on other life forms is less clear, but increased radiation could potentially lead to mutations and genetic damage, with unpredictable consequences for ecosystems. Section 7. The Atmosphere in Peril. The weakening magnetic field could also have implications for our atmosphere. This magnetic field, generated by the movement of molten iron in Earth's outer core, acts as a shield, protecting our planet from the solar wind. Without this shield, the solar wind, which is a stream of charged particles emitted by the sun, would have a more direct impact on our atmosphere. With less protection from the solar wind, the atmosphere would be bombarded by charged particles, gradually stripping away its outer layers. This stripping process is not immediate but occurs over an extended period. The solar wind can erode the atmosphere by knocking atmospheric particles into space, a phenomenon observed on planets like Mars, which has a very thin atmosphere due to its weak magnetic field. This process would be slow, happening over millions of years, but it could eventually lead to a thinner, less protective atmosphere. The gradual loss of atmospheric particles would mean that the atmosphere becomes less dense, reducing its ability to shield the surface from various space weather phenomena. A thinner atmosphere would offer less protection from harmful ultraviolet radiation from the sun, further endangering life on Earth. Ultraviolet radiation can cause severe damage to living organisms, including increased rates of skin cancer in humans and harm to the DNA of various life forms. The ozone layer, which absorbs and scatters the majority of the sun's harmful UV radiation, would be less effective in a thinner atmosphere. The loss of atmospheric gases could also impact Earth's climate, potentially leading to changes in temperature and weather patterns. A thinner atmosphere would mean less greenhouse gases, such as carbon dioxide and methane, which are crucial for maintaining Earth's temperature. This could result in a cooler planet, altering ecosystems and affecting agriculture and water resources. The exact nature of these changes is difficult to predict, but they could have significant consequences for life on Earth. Scientists are continuously studying these potential impacts to better understand how our planet might change and to develop strategies to mitigate these effects. The future of Earth's atmosphere is uncertain, but understanding these processes is crucial for preparing for and potentially preventing adverse outcomes. Section 8. Life on the Edge. While a sudden and complete shutdown of Earth's core is unlikely, even a gradual weakening of the magnetic field could have profound implications for life on our planet. The increased radiation exposure, atmospheric loss, and potential climate changes would create a more hostile environment for many life forms. Some species might adapt, while others could face extinction. The impact on human civilization is difficult to predict, but it would undoubtedly be significant. We rely on technology that is vulnerable to radiation, and our society is built on a stable climate. A changing Earth would require us to adapt and innovate to survive. Section 9, a silent warning. The hypothetical scenario of Earth's core stopping is a stark reminder of the delicate balance that supports life on our planet. Imagine a world where the very heart of our planet ceases to function. The core, a molten iron dynamo, is crucial for generating the magnetic field that shields us from harmful solar radiation. The seemingly solid ground beneath our feet is anything but static. Beneath the surface, a dynamic and ever-changing environment exists, driven by the movement of tectonic plates and the flow of molten rock. This geological activity is responsible for earthquakes, volcanic eruptions, and the creation of mountain ranges. Deep within Earth, forces are at work that shape our world in ways we are only beginning to understand. Magma, the molten rock beneath the crust, moves and shifts, creating new landforms and altering existing ones. These movements are a testament to the planet's constant state of flux. The core's rotation, the magnetic field it generates, and the protection it provides are all interconnected parts of a complex system. This magnetic field not only shields us from solar winds but also plays a crucial role in navigation for both humans and animals. Without it, life as we know it would be drastically different. By studying the core, we gain a deeper appreciation for the preciousness of our planet and the importance of protecting it. Researchers use advanced technology to peer into the depths of the Earth, uncovering secrets that help us understand the past and predict future changes. Understanding the forces that shape Earth is essential for our continued survival. As we learn more about these powerful processes, we can better prepare for natural disasters and mitigate their impacts. This knowledge is vital for developing strategies to protect our environment and ensure a sustainable future for generations to come. Section 10, Mysteries of the Deep. Despite advances in technology, Earth's core remains largely a mystery. We cannot drill deep enough to sample it directly, so we rely on indirect methods to study it. Seismology, the study of earthquakes, provides valuable clues. By analyzing the way seismic waves travel through Earth, scientists can infer the composition and structure of the core. Other methods, such as laboratory experiments that recreate the extreme pressures and temperatures found in the core, also contribute to our understanding. Yet, many questions remain unanswered, driving further research and exploration. Section 11, Our Planet's Future. The fate of Earth's core is inextricably linked to the fate of our planet. As we continue to learn more about the core, we gain a deeper understanding of the forces that shape Earth and the challenges we face. Climate change, resource depletion, and other environmental problems pose significant threats to the delicate balance of our planet. By understanding the interconnectedness of Earth's systems, we can make more informed decisions about how to protect our home. The study of Earth's core is not merely an academic pursuit but a vital endeavor that can help us safeguard the future of life on Earth. Look up at the sky. Have you ever wondered about the vastness above us? The stars, the planets, and the endless expanse of the universe? It's a mesmerizing sight, one that has captivated humanity for millennia. The sun rises in the east and sets in the west. This daily ritual is something we often take for granted, yet it is a fundamental part of our existence. Each sunrise brings a new beginning, and each sunset marks the end of another day. This happens because our planet is constantly spinning, like a top dancing on its axis. Imagine a child's toy, spinning endlessly, never losing its momentum. That's our Earth, tirelessly rotating, creating the rhythm of day and night. We call this movement Earth's rotation. It's a simple term for a complex and vital process. This rotation is what gives us our sense of time, dividing our days into light and darkness. This rotation is fundamental to life as we know it, dictating day and night and influencing everything from weather patterns to ocean currents. The spinning Earth affects the winds, the rains, and even the way our oceans move, creating currents that sustain marine life. Earth's rotation is a continuous movement, a never-ending spin that has been happening for billions of years. From the moment our planet formed, it has been in motion, a dance that has shaped the very fabric of our existence. This spin is not something we feel directly, like the rumble of an earthquake or the rush of wind. It's a silent, invisible force, one that we can only observe through its effects on our environment. Instead, it's a silent, invisible force that shapes our world in profound ways. From the gentle sway of the trees to the powerful currents of the oceans, Earth's rotation is a constant, guiding force in our lives. It reminds us of the delicate balance that sustains life on our spinning world. Imagine a basketball spinning on your finger. The ball twirls effortlessly, maintaining its balance as it rotates. This simple act is a perfect example of rotational motion, a concept that is fundamental to understanding how objects move in a circular path. Every point on the ball makes a complete circle in the same amount of time. Whether it's the top, bottom, or any point in between, each part of the ball follows a circular trajectory, completing one full rotation simultaneously. This is the basic principle of rotation, a circular movement around a fixed axis. The axis is the imaginary line that the object spins around, and it remains constant as the object rotates. The Earth rotates on its axis, an imaginary line passing through the north and south poles. This rotation is what gives us the cycle of day and night, as different parts of the Earth face towards or away from the Sun. This axis of rotation is not perfectly straight up and down but tilted at an angle of about 23.5 degrees. This tilt is crucial for the diversity of climates and weather patterns we experience on our planet. This tilt is what gives us our seasons. As the Earth orbits the Sun, the tilt causes different parts of the Earth to receive varying amounts of sunlight at different times of the year. As Earth spins, different parts of the planet receive varying amounts of sunlight throughout the year, creating a dynamic and ever-changing environment. This variation in sunlight is what drives the changes in temperature and weather patterns, leading to the familiar cycle of spring, summer, fall, and winter. Each season brings its own unique characteristics and changes, from blooming flowers in spring to the falling leaves of autumn, all thanks to the Earth's continuous dance of rotation and tilt. Our planet is not a perfect sphere. It's slightly wider at the equator and flatter at the poles. We call this shape an oblate spheroid. This shape is important because it means that points on the equator have a longer distance to travel in one complete rotation compared to points closer to the poles. Think about it like running a race. If you're running around the outer edge of a circular track, you'll cover more ground than someone running on a smaller, inner lane. Similarly, a point on the equator travels a greater distance in one rotation than a point near the North Pole. Imagine swinging a ball tied to a string. As you spin it, you feel a force pulling outward on the string. This force is called centrifugal force. It's the same force that pushes you to the side when a car makes a sharp turn. Earth's rotation also creates centrifugal force. This force is strongest at the equator, where the distance traveled in one rotation is greatest. The centrifugal force is weaker at the poles because the distance traveled is shorter. Section 5, From Equator to Poles, a Change of Pace. Because of the Earth's shape and the centrifugal force, the speed of rotation is not the same everywhere on the planet. The equator, being the farthest point from the axis of rotation, spins the fastest, at roughly 1,000 miles per hour. As you move towards the poles, the speed gradually decreases. This is because the circumference of the Earth gets smaller as you move away from the equator. At the poles themselves, the speed of rotation is essentially zero. Section 6, Whizzing Through the Atmosphere, Weather and Rotation. Earth's rotation has a profound impact on our weather patterns. One of the most significant effects is the Coriolis effect. This effect causes moving objects, like air masses, to curve as they travel across Earth's surface. In the northern hemisphere, the Coriolis effect causes winds to curve to the right. In the southern hemisphere, winds curve to the left. This deflection of winds influences the formation of large-scale weather systems, such as hurricanes and cyclones, which spin in opposite directions depending on the hemisphere. Section 7. Time flies when you're near the equator, travel and rotation. The difference in rotational speed between the equator and the poles has a subtle but measurable effect on time. According to Einstein's theory of relativity, time slows down slightly in stronger gravitational fields. Because the centrifugal force is stronger at the equator, the effective gravitational pull is slightly weaker. This means that time actually moves a tiny bit slower at the equator compared to the poles. The difference is minuscule, only a few nanoseconds per day, but it's a real phenomenon. You might wonder why the Earth doesn't simply fling itself apart with all this spinning. The answer lies in a delicate balance of forces. Gravity, the force that pulls everything towards the center of the Earth, acts as a counterbalance to the outward push of centrifugal force. Gravity is a much stronger force than centrifugal force. It's what keeps our planet together and prevents us from flying off into space. This balance between gravity and centrifugal force is essential for maintaining Earth's stable shape and rotation. Earth is not the only celestial body that rotates. In fact, almost everything in space spins, from planets and moons to stars and even galaxies. The speed and direction of rotation vary widely depending on the object's size, mass, and history. Our Sun, for example, rotates on its axis about once every 25 days. However, the Sun's rotation is not uniform like Earth's. Because it's a giant ball of gas, different parts of the Sun rotate at different speeds. This differential rotation plays a role in the Sun's magnetic activity, which can lead to solar flares and sunspots. Earth's rotation is a fundamental aspect of our planet's existence. It influences our daily lives in countless ways, from the rhythm of day and night to the patterns of our weather. It's a testament to the intricate workings of the universe, where even seemingly simple movements can have profound and far-reaching effects. As we continue to explore and understand our place in the cosmos, it's essential to appreciate the fundamental forces that shape our world. Earth's rotation is not just a scientific fact, it's a reminder of our planet's dynamism, its constant motion, and its interconnectedness with the vast universe around us. Our planet is a spinning sphere, a celestial dancer whirling through the vastness of space. This constant rotation is a mesmerizing ballet that has been ongoing for billions of years, ever since the Earth first formed from the dust and gas of the early solar system. This rotation, a fundamental characteristic of Earth, dictates the rhythm of our days and nights, shapes our weather patterns, and even influences the flow of time itself. As the Earth spins, it brings about the cycle of sunrise and sunset, creating the beautiful transitions from day to night that we experience daily. The rotation also plays a crucial role in the formation of weather systems, driving the winds and ocean currents that regulate our climate. From the equator to the poles, the speed of this spin varies, a testament to the interplay of forces that govern our planet. At the equator, the Earth spins at its fastest, completing a full rotation in just under 24 hours. However, as you move towards the poles, this speed decreases, illustrating the complex dynamics of rotational motion. This variation in speed is due to the shape of the Earth, which is not a perfect sphere but an oblate spheroid, bulging slightly at the equator. As we've explored, the Earth's rotation is not just a solitary phenomenon. It is part of a larger cosmic dance, influenced by the gravitational pull of the Moon and the Sun. The Moon's gravity causes the Earth to wobble slightly on its axis, a motion known as precession, which affects our planet's orientation in space over long periods. It's a reflection of the interconnectedness of the cosmos, where celestial bodies from planets and moons to stars and galaxies are engaged in their own intricate dances of spin. Each of these bodies, whether a small moon or a massive galaxy, follows The same fundamental principles of physics, creating a harmonious and interconnected universe. The rotation of planets and stars generates magnetic fields, influences their atmospheres, and even affects the potential for life. Understanding these forces allows us to appreciate the delicate balance that sustains our world and deepens our connection to the universe we inhabit. By studying the rotation of Earth and other celestial bodies, we gain insights into the fundamental workings of the cosmos, revealing the intricate and beautiful patterns that govern our existence. This knowledge not only enhances our appreciation of the natural world but also inspires us to explore further, seeking to uncover the mysteries of the universe and our place within it. Thanks for watching. Don't forget to subscribe, like, comment and share.